In section 8.1, we explore a new function type called the exponential function, which involves the expression b to the x power, where the base b is a positive number other than 1. So right now we will be looking at exponential functions for which b is greater than 1. These would be called exponential growth functions. So remember now, if b was 1, when we take 1 to different powers, right, because you see our variable is an exponent, if we take 1 to different powers, it doesn't change the output, so that would really just be a linear function. So that is why b must be a number other than 1. Okay, and this is what an exponential growth function looks like. As we look at how the graph heads out toward the left, that's toward negative infinity. As x approaches negative infinity, my graph becomes very flat. And as x approaches positive infinity, meaning we're moving to the right, my graph turns toward going vertical. So if we're looking at creating an input-output table that will help us graph this sort of shape, I know that toward the left it's very flat, and toward the right it's vertical. And I need to graph this curve in between. So we're going to look at what are the best points that I should pick in order to find these points that will define this curve. So if you look over here, this is an input-output table that deals with taking 2 to different powers. So our function is f of x is equal to the x power. And you can see that as I have negative exponents, my outputs are very, very small. And as I have increasing positive exponents, my output becomes very, very large. Okay, now you can also see that this is a line right here. This end of the graph will keep getting smaller and smaller and smaller, right? I'll have 1 over increasing powers of 2. So it'll keep approaching 0, but it will never actually reach 0. So this becomes a boundary line or a limit. Okay, and that limit is called an asymptote. The asymptote is a line that my graph approaches as I move away from the origin. It will keep approaching the asymptote, but it will never, ever actually hit it. So in terms of vocabulary here, we've got the new definition of a function, an exponential function, which looks like b of x, y is equal to b to the x power, and asymptote, which is a line the graph approaches as you move away from the origin. When we look at graphing these, in this case it's in a very simple form, what I would do is I would do an input-output table. And what's going to help me find the best points to help define this curve, once I move into negative exponents, that inverts my base, so it starts approaching 0. And when I use positive exponents, it becomes increasingly large. And then when my exponent is 0, that will also be informative. So I'm going to choose -1, 0, and 1, because they will give me good points to define this curve. Okay, so when I plug -1 in here, 5 to the -1 power is 1/5, times -2 is -2/5. 5 to the x power when x is 0, 5 to the 0 power is 1, times -2 is -2, and 5 to the first power is 5, times -2 is -10. When I go ahead and graph that at -1, I'd be at -2/5, right there. At 0, I'd be at -2, and at 1, I'd be at -10. But this doesn't follow the shape that I talked about. Yes, over here it's very flat. It is approaching 0 but not getting to it. And over here it's essentially vertical, but it's flipped over. So if we go back and compare it to the previous graph, you'll see this graph was flat on the left and vertical on the right, but it was going up, where in the new graph, it's going down. And what made that change? What made the change is the leading coefficient. See, just like many of our other graphs, when the leading coefficient is negative, it flips the graph over, and now instead of trending upward, it trends downward. So this is the same thing you discovered with quadratic functions, and it was also a rule that we followed when we looked at end behavior of larger polynomials. Okay, now that was in a very simplified form. Now we're going to look at a full form, and you'll notice that the variables h and k are back in. Now, h, you'll see, always travels with x. So x has moved, x has become an exponent, and you'll notice that h moved with it. And h is also part of this expression that creates an exponent, x minus h. And k, again, is on the right side by itself because it's related to y. So again, you could think of this as y minus k is equal to a times b to the x minus h power. Okay, and this makes it a little more plain that k is again a change, a vertical change in the y-axis, and h is a change in the x-axis. So just as we did in our power functions, when we graphed square root and cube root functions. So just as we did when we graphed square root and cube root functions, we are going to identify h and k. Then we'll create an input-output table without h and k, and then we will move the graph by the values of h and k. So the same steps that you followed for square root and cube root functions, we will follow for these. So the first thing I would want to do is figure out what h and k are. You'll see that h here is being subtracted from x, h is 1. And k, there's nothing being added on or subtracted over here. There's nothing paired up with y over there. K is 0. Okay, so I figured out that h is 1 and k is 0. And now I'm going to move on and I'm going to go ahead and graph this without h and k. So to graph it without h and k, excuse me, didn't want a red pen. So to graph it without h and k, I'm going to create an input-output table using this simplified version, 4 times 5 to the x power. Okay? And I'm going to use the same inputs that I did before, -1, 0, and 1. 5 to the -1 power is 1/5 times 4 is 4/5. 5 to the 0 power is 1 times 4 is 4. And 5 to the first power is 5 times 4 is 20. Okay, so I've got 3 points to help me define the curve. And I think what I'm going to do, because my graph is basically in tens, is I'm going to make this go by 2s. So over here at -1, I would be at about 4/5, which would be about, say, there. And at 0, I'd be at 2, 4. And at 1, I'd be all the way up at 20. So you'll see this is going to rise very, very rapidly. I'd come in flat here, pass through these points, and that's my graph. Now, that's without h and k. Now I want to shift it by h and k. So h was 1, that means 1 unit to the right. And k was 0, so there's nothing up and down. So if I take each point and I move it 1 to the right, 1 and 1, you'll see that I have a very close to the same graph. And there we are. Okay, so identify h and k, then create an input-output table without h and k, graph it without h and k, and then shift by h and k. In this problem, I see that h is equal to -1, because this is x minus -1. In this problem, I see that h is equal to -1 because this would be the same as x minus -1. And k is 1. So h is equal to -1 and k is equal to 1. Now I'm going to graph it without h and k. Y is equal to 3 to the x power. Here's my input-output table. I pick the same values again, -1, 0, and 1. And here I'll have 1/3. 3 to the -1 power is 1/3. 3 to the 0 power is 1. And 3 to the first power is 3. So I'll have 1/3, 1, and 2, 3. I go ahead and run my graph through this. And now I want to shift it 1 to the left and up 1. So I'm going to take each of these points and go 1 to the left and up 1, 1 to the left and up 1, 1 to the left and up 1. And there's our final graph, including my shaky handwriting. Okay, so identify h and k, create an input-output table without h and k, graph without h and k, and then shift the graph by h and k. Same thing we did again with square root and cube root functions. Okay, another thing that we can do with exponential functions is we can explore interesting things with financial information. Exponential growth can also be used to model a percentage change annually and how that compounds. So we're not talking about, in the case of financial issues, we'd be talking about compound interest instead of straight interest. But there are other issues that can be modeled with this type of an exponential growth function. So the formula that we would use is y is equal to a times 1 plus r being the rate, to the t power where t is time. Okay, now your rate and your time would need to be the same. So if you're talking about years, then you'd be needing a rate of change in years. So if we look at this problem, in 1980, wind turbines in Europe generated 5 gigawatt hours of energy. Now this is our starting situation. Okay, that would be this A value right here. In a financial model, it might be labeled as P for principal, the initial amount of money in a bank account. In this case, it's the starting situation at a given point in time. So over the next 15 years, the amount of energy would increase by 59% per year. 59% would be our rate. Now make sure a percentage, when you write a percentage, really that's another way of expressing a decimal. When you put the percentage into this model, you must put it in as a decimal, not as a percentage. Okay, so I'm going to put in 0.59 when I write this out. So write a model giving the amount of energy E, so E would be equal to my starting situation, 5, times 1 plus my interest rate, or sorry, my growth rate, 59%, to the t power. That's my model. So the energy in any given year t can be found by 5 times 1.59 to the t power when I simplify what's in parentheses. Now what's also going to be important is that when you think about this, you need to look at t is going to be not just years, it's going to be the number of years since 1980, right? So 1980 is the 0 year, right? Because if we put 0 in, 1.59 to the 0 power times 5 will equal 5, and 5 was the energy hours in that particular time. Okay, so when we want to look at how much wind energy was generated in 1984, we'll have E is equal to 5 times 1.59 to the 4th power, because 1984 is 4 years after 1980. So I'll take 1.59 to the 4th power, and then I would multiply it by 5. And in this case, the energy is going to be 31.96. Okay, so in 1980, 5 gigawatt hours of energy. In 1984, 31.96. So as I mentioned earlier, we can use this same formula, only in expanded form, to calculate compound interest. The only thing that's new now is we've added this variable n. R is still the rate, it's still a percentage. P is the principal, that's the starting situation, or in this case, the amount of money I put into a bank account initially. A is the account value, and this new n item is the number of times per year that we compound the interest. So sometimes interest is compounded daily, it can be compounded weekly, monthly, quarterly, annually. So each different situation is going to yield a slightly different result. So t is still time. If I want to go ahead and write a model here, I want to have $2,500 after 2 years. So this is the A value, the amount I'm going to finish with. This is the amount I want to have at the end of 2 years. Find the amount of money I need to deposit in an account for each of several different situations. We're going to do 3 just so you can get a sense of how compound interest changes things. So I know that this $2,500 will be equal to an unknown amount of money, P, that I'm going to deposit in an account. And I have a rate, this is my annual interest compounded monthly. So my rate is 2.25%. That would be 0.0225 as a decimal. And my end value, because we're compounded monthly, would be 12, because we're compounding 12 times per year. The 12 goes there in the denominator, and it also comes up here. And then t is the number of years, so after 2 years. Okay, when I simplify this, I'll get that the amount I'm looking for is still $2,500, is going to be equal to P times 1.001825 to the 24th power. When I go ahead and take this to the 24th power and then divide 2,500 by it, I'll get P is equal to 2390.09. Now it's money, so I'm rounding to the nearest penny. So this is the amount I would have to deposit at 2.25% interest to finish with 2,500 after 2 years. You notice over 2 years, with this very low interest rate, you earn very little money. Okay, so let's take a look at how changing the interest rate and changing how frequently we compound impact the situation. So in this case, we're going to look at 2% less interest compounded quarterly and also compounded less frequently. So in this case, my $2,500, principal 1 plus 2%, 0.02, compounded quarterly would be 4. And the 4 goes up here, and it's still 2 years. So this is going to be P times 1.041 to the 8th power. No. So this is going to be $2,500 is equal to P times 1.041 approximately. So the amount I would need to invest would be even more, $2,402.21. Now it's important, when I actually take this to the 8th power, when I took the other power to the 24th power, I end up with a rather large decimal. It's important that you don't round the decimal if you don't have to. So remember, you can transfer a calculation that you've used in your calculator to the next problem by using the second key and the negative sign, the opposite that's down next to the decimal place. Okay, so if you do second opposite, it'll take the answer from the previous calculation and plug it into your equation. In this case, I would have done 2,500 divided by second key, opposite key, enter in my calculator so that I could transfer this without rounding it. Because if I round it, I'm going to introduce error and I'm going to come up with a very different number here. Okay, that's the difference between the actual calculation and the result you get when you round is called rounding error. Right, and our last example, we've increased the interest rate, but we've decreased how frequently we compound. So I'll still have $2,500 equal to some unknown amount of principal times 1.05, that's 1 plus the 5% interest. We're compounding annually, so my denominator here would have been 0, and it's to the second power. Right? This will become p times 1.1025 or so. And when I divide by that, I'll get my principal amount, 2267.57. Okay? So this finishes up our section 8.1. And what it's important for you to understand is that the more frequently you compound with the same interest rate, the more money you will have. However, the part of the equation that impacts the amount more is the interest rate. More than how frequently you compound, what impacts the value is going to be the interest rate.